Okay, so these couple of questions are coming from Chapter 10. And in more particular, this is 10.3. So this is 10.3. All right, so we're going to look at a couple of numbers here that some students had some questions on. So the first one was number 46. Now, the first thing I see here is we want to know what the probability of A and B is. And that's if A or B is 0.6. But before we do that, we need to make sure we know the rule. So one of the rules is probability of A and B is going to be the probability of A and that's going to be plus the probability of B. But what we have to remember is since there's an there could possibly be an intersection there, and it does say there's an intersection, A or B is 0.6. And so what we want to do is we want to make sure we take out any duplicates. And so we have to subtract the probability of A or B. And the reason why we have to subtract that is because if I add the probability of A, that already includes the A or B, because A or B, that's the overlapping part. And then the B also includes that. So we want to make sure that we don't add that part in twice. And so in the directions it says probability of A is 0.25, probability of B is 0.45, and that union, A or B, the union part, is 0.6. And so add those together, and we got 0.25, 0.45, that's 0.7 minus 0.6. And so we get a final answer of 0.10. And that was for number 46. All right, so now number 48. So 48. All right, so number 48. This one says probability of P, or excuse me, probability of A and B, in A intersection B, A and B, if A and B are mutually exclusive. Well, this one's actually really easy. So if you have the probability of A and B, we basically want to know the probability of them occurring, I guess you would say at the same time. I guess that's the best way to say this. But if they're mutually exclusive, they won't ever occur at the same. There's no intersection. So if they're mutually exclusive, and we want to know when they occur at the same time, A and B, well, this is going to always be 0 if they're mutually exclusive. That's just a general rule of probability. All right, so number 71 was also in question. So let's look at 71. Now for number 71, it says, what is the probability that at least 2 people have the same birthday in a group of 12 people? Assume that there are 365 days in a year. Oh boy. So probability of at least 2 with the same birthday. Well, there's a couple ways we can probably go about this. I guess the best way we can do it is actually change the perspective of this problem. So if we try to change this perspective, we have to remember that the overall probability is always 100%, 1 basically. So instead of trying to find that, if I did 1 minus the probability of none with the same birthday. So if we're looking at none with the same birthday, so none with the same birthday. Now think about it. So this is saying at least 2 people have the same birthday. Well, what that means is, it could be 2, 3, 4, 5, 6, all the way up to all 12 having the same birthday. But if you think about it, so if we say the probability that they don't have anything in common, none of them have the same birthday, well, that's basically every individual one has a different birthday, which is a very easy case to try to find. Versus going through and trying to find the intersection of 2 and then 3 have the same birthday, then 4, then 5, then 6, 7. Instead of doing all those multiple steps and adding all those probabilities at the end, well, we can do it a little easier. We take the whole, which is 1, and subtract the probability that none have the same birthday. And so, since I said at least 2 people, well, if you go less than 2, that means one person has the same birthday as itself. Doesn't make it, so that's why I'm saying none. So 2 people have the same birthday. So hopefully that wasn't confusing. Don't mind me. So what is probably at least 2 people? Well, if you go any less, then obviously none have the same birthday. That's what I was trying to say. All right. So what we have to do is we have to find basically the different birthdays. So this is like basically saying the sample space here. So we have the sample space for different birthdays. And that's going to be divided by the sample, the set, or the whole set, like all the possibilities. And so that, and you might see this here in the book. And all that's saying is, okay, so we have 12 people. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, the first person, well, if they would have 365 days. All right, so if we're just looking at the first person, but now, if they don't have the same birthday, well, what happens is 365, well, there's 364 other days. Well, that's about 364 other days that that person might have a birthday. Now, again, if none of them have the same, 2 of them are already taken, so then it's 363. That's how many days are left for the other person to have a birthday. Any of those other 363 days. And this goes all the way on to 365, 354. That would be the 12th person. And so that would be 63, 62, 61, 60, 59, 58, 57, 56, 55, 54. And so it would be all those numbers. And now by multiplication principle, we would multiply all these for all the different possibilities. Now I didn't write out all those numbers, but basically it's counting all the way down to 354. And so that would be what's on the top. Now on the bottom though, we need to know the whole sample space, the whole entire, every possibility. And every possibility includes them overlapping, having the same birthday, not having the same birthday. And that one is actually going to be a very large number. But that one's also very easy to calculate. So in the sample space, if I just look at each individual person, 365 days, what's the probability that basically one person has any given day? It's 1 over 365. And the next person would also be, any given day would be 1 over 365. And so on. That would be 12 times. So that's 1 over 365 to the 12th power. So on the bottom there, we're going to have 365 to the 12th power, because that's just looking at the entire sample space. That regardless of overlap and same birthdays, no same birthdays, we're just simply looking at, hey, each individual person, has a 1 in 365 chance of having any given day for a birthday. And that occurs 12 times. And that's why we have an exponent of 12. And so put this all together here. Basically, this part's going to be in the numerator. And then in the denominator, we have the 365 to the 12th power. So on the top, we have 365 times 364. I'm going to put dot, 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 all the way to 354. Oh boy. Well, let's see what that ugly mess comes out to be. Let's bring up that calculator here. All right, here we go, calculator. And so let's do, now, most people actually do all the multiplication straight out, which is perfectly fine. There's other ways to do it too, but we'll just do it all the way out. Just say consistency and keep it simple. Ooh, 363, hello. 362, 361, 360, 359, 358, oh boy, 357, 356, 355, one more. Let's just make sure we got them all. 65, 64, 3, 2, 1, 0, 9, 8, 7, 6, 5, 4. And that's, now see, that's just a really large number. That E is just scientific notation. So we're going to take that number. We're going to divide that number by 365 raised to the 12th power. And that ugly thing just comes out to a nice little decimal here. We're around to, I'm not sure if the direction's set it up, but we'll just do 3 decimal places. So this is approximately 0.833. So approximately 0.833. So with all that said, what we're going to do now is we're going to go 1 minus that 0.833. And so what this did once again was we took the whole. We took the entire thing, the whole of 100%, every possibility. And we're subtracting the probability that none have the same day. And so that's what we got with the 0.833. And so there's going to be 1 minus 0.833, which is, let's do it real quick in the calculator here. 1 minus 0.8, which is 0.167. 0.167. Now that one was probability is a tough topic, and that was a little weird to try to get there. Just one more time. So what we had there was we were looking at the whole, subtracting the probability of getting of nobody having the same birthday. So to get nobody, again, every individual person has a different day. And so that's where we came down here and we said, all right, well, the first person has 365 days. Well, if that one person has a day taken, next one's 364, 363, all the way down to 354 to have all 12 people represented. And so that's what we did to get the basically the number of possibilities for none having the same birthday. And then we have to look at the total sample space, because what we have to do with probability is look at the number of successes. In this case, since we're trying to find a probability of none having a birthday, and that's going to be over the total population, or the total sample space, or total possibilities. And to get that for this one here, it was going to be the 365 to the 12th power. Because if we look at the entire range of possibilities, with also including overlap and same birthdays, it'd be 365 times 365 times 365, 12 times basically. And so that gives us the full number of possibilities. And so that's why we did this here. We did 365 times 364 all the way down to 354 over 365 to 12, and that's where we got the 0.833. And again, this was 1 minus the probability of having none with the same birthday. And so that's how we ended up with probability of at least 2 having the same birthday. This is 1 minus the probability of none having the same birthday, because they all have to add up to 100%. So if the probability of getting for no one to have the same birthday is 0.833, well, 0.167, that's the probability of having at least 2 people with the same birthday. And if you add those up, you do end up getting back to 100%, a whole percent. All right, and so these numbers here were from 10.3, number 46, 48, and 71.